Hi, I'm Krishna. This is day 11 of 30 days of understanding the modern AI stack. So, in this video, we're answering a question that should bother you if you really understand transformers. Transformers process every word at the same time, parallel, no recurrence, no left to right reading like RNNs. So, how does the model know that I love you is different from you love I? कि मैंने तुमको प्रेम किया कि तुमने मुझको प्रेम किया? If attention treats tokens as just vectors and dot products don't care about order, then language should collapse into a bag of words. So something must be injecting order into the system. That something is positional embeddings. Let's slow down and think. Each word becomes a vector. Attention computes q dot k, query dot key. Dot products measure similarity. But similarity alone does not encode position. If I shuffle tokens but keep the same embeddings, attention sees the same set of vectors. So transformers are naturally permutation invariant. But language is not permutation invariant. So we must break that symmetry. And here's the cleanest solution. Add position into the embedding itself. So instead of just token embedding, we compute token embedding plus positional embedding. Now pause. Why does addition even work? Because attention doesn't see tokens directly. It sees projections where Q query is equal to token plus position multiplied by weight matrix and K is equal to token plus position multiplied by weight matrix. That means both content and position influence attention scores. When attention compares tokens, it's comparing meaning, where they appear, how far apart they are, or inside one dot product. So position gets baked into the same vector space. That's elegant. But what are these positional embeddings exactly? There are two major types. First, the original transformer used sinusoidal encoding. Instead of learning position vectors, it computed them using sine and cosine waves of different frequencies. Why sine and cosine? Because they are smooth. They generate unique patterns for each position. Relative shifts can be inferred mathematically. Lower dimensions capture broad position patterns. Higher dimensions capture fine-grained shifts. It's like layering waves of different frequencies to uniquely encode position. Now, modern models like GPT mostly use learned positional embeddings. Instead of math formulas, they simply learn position 0 is a vector, position 1 is also a vector, and position 2 is also a vector. Same concept but different implementation. Goal remains the same, break permutation symmetry. Now you might think, okay, so the model now understands order. So we are done, right? Not quite. There's another problem. The cheating problem. When training GPT, we feed full sentences. Example, I will go to the market. If the model can see market while predicting market, training becomes trivial. It just copies. But during inference, future tokens don't exist. So training and inference would mismatch. That's why we use masking. Now causal mask, which enforce time. We apply a triangular mask. So token 1 sees only token 1. Token 2 sees 1 and 2. Token 3 sees 1, 2 and 3. Never future tokens. Mathematically, we add negative infinity to forbidden attention scores before softmax. Softmax turns those into 0. So the model literally cannot look into the future. This enforces probability of next token given that we have previous tokens, which is real language modeling. Second one is padding mask, cleaning noise. When batching sentences, we pad shorter ones. If not masked, the model may attend to padding tokens. So we mask them too. We have two masks, causal mask, which enforces time direction. Padding mask, ignore fake tokens. Both are constraints applied before softmax. So a transformer needs meaning, token embeddings, order, positional embeddings, direction, masking. Without positional encoding, it is just a bag of words. Without masking, cheating. Without both, GPT doesn't work. So it's not magic, it's just controlled math, where positional embeddings give transformers order and masking gives them time. Together they turn parallel computation into real language modeling. So see you in the next video. Let's do it.